All right, sorry. Good afternoon. Let's start. Okay. Okay, so we're gonna look at a new topic today. Okay, we'll look at basically another part of the shaft design, which is basically the key designs here. Okay, yeah. The keys, as you probably noticed in the previous lecture, basically when we talk about shaft will need to transmit torque, okay, or being transmitted torque from another element, and the key is basically the coupling between the shaft and the element that is called the component the shaft is carrying. Okay, so for example, if this is a shaft here, and then you have a key, then you probably have another elements, okay, on the top of this shaft that is here, and which we call the hub. Okay, the hub is probably part of a gear or part of another mechanical component, but the torque is being transmitted, okay, through this case that is here, so between the shaft and the hub. So when we talk about the key, okay, essentially the function of the key, functionality for key is to transmit the torque, okay, and the key is typically between a shaft and the hub. Okay, so that's a functionality of the key. Yeah. There are three different keys. We're going to look at it. Okay. Yeah. One is the so-called parallel key, taper keys, and this Woodruff keys at here. Okay. And the objective for us, okay, it's basically is to pick up a key with proper size, okay, and shape. So you can either pick a parallel case, or you pick a taper case, you'll pick a Woodruff case. Okay, it doesn't matter, but it needs to be appropriate size. So, for example, if you're a parallel case, the size basically means what will be the W, what will be the H, and what will be this L at here. Okay, so that's the basically design parameters for deciding on the appropriate K. Okay, so we'll look at a number of details here. Our focus is actually on parallel case at here. Okay, yeah. Parallel case is pretty straightforward. Basically, the geometry is a rectangular. If you cut a cross section, taper key, the shape is definitely looks different. There are two different type of ending in here. One is so-called plain ending. The other is called the gib case here. So this is basically a gib type. It has an inclination. Okay. That's why it's tapered, and the inclination is actually 1/8 inch per foot. Okay, so that's actually standard. Okay, yeah. Woodruff key, we'll have an example in the tutorial next week. So Woodruff key, basically, it's very useful. It's usually smaller size. It's very useful if you have a smaller size of a shaft. Okay, and you can use a Woodruff key for torque transmission. Okay. Okay, so let's look at this parallel key. Okay. Most of the design at here for picking a key here, you need to look up the tables, and you need to calculate basically the so-called minimum length of the key. Okay, so the tables we're referring to, there are a number of tables that are here. Okay, this is the first table showing it here is a table 7-6 in your textbook. Okay. So if you look at this table here, what it tells you is a number of information that are here. Okay, the column on the left side, okay, give you a range of the shaft diameter. So shaft diameter between 7/16 to 9/16, right, or from here to here. And then it recommends that the K, the rectangle K or parallel K, the W should take this 3/36, and H should take 3/36. 30 seconds, right? Yeah. Now, if you look at, for example, the second row right here, right? If shaft size is between 7/16 and 9/16, you can pick K with a W equal to 1/8 and H equal to 30 seconds, or you can pick your W to be 1/8 and H to be 1/8. So basically, there are two choices here, right? The first choice, okay, is what we call rectangular key, and the second choice is what we call a square key. Okay? So this is basically, you can have two choices sometimes. Okay? And there's another figure and I'll show you later. Okay? And there is a recommended basically size for whether rectangular or square that you should take. Okay? So but either way, okay, so basically bear in mind this is your W at here, and this is your H at here. Okay, this is H. Okay, and the last column says the KV depths. So KV depths basically is where you plug your case into the case state. So this portion is the KV depths. Okay, and it's typically just 1/2 of the H. So that's, if you look at this number, that's 1/2 of the H value here, right? So that's the K state depth basically. That's table 7-6. Okay. Yeah. And there's another one given in my lecture notes, but not in the textbook. Okay, so this is in the lecture notes. This one here, a little bit more information. Okay, this table is in lecture notes. Very similar to the table 7-6. Okay, very similar. Now, except there is a recommendation underneath the table here. What it's saying is, okay, values in the non-shaded area are preferred. So the values in the non-shaded area are preferred. So as you can see, when the case is actually the diameter of the K, right? If it's less than 6.5, right? So if it's less than 6.5, non-shaded is this square part. So if the shaft size is less than 6.5 inch, then it's recommended that you use square K. If it is more than basically 6.5 at here, then recommended to use rectangular K at here. Okay, so that's basically what this table here. Otherwise, the numbers are pretty much the same as 7-6. Okay. Now, another table in the textbook, and I'll give it to you, is from a different textbook. This is from the Robert Norton's textbook. Okay. So from this textbook, it's very similar. So you give you a range of shaft diameter, and then there's recommended the K width W. Okay, over here. Okay, but this is not in terms of, instead of giving you the fraction, it's in decimal numbers at here, right? Yeah. And there's also instead of the inch series, also give you metric series number at here for the case size. Okay. So one of the assignment question, I would in assignments I actually recommend you use this table here. If you have a metric size given, use this table to come up with the recommended K width or K size. Okay. And then another information in this table is the so-called set screw diameter. Okay, so if you have a gear, you have a shaft, then you put the case on the shaft, then you're sliding the gears right through the shaft, okay, and on the top of the case. Okay, then how would you fix the gear to the shaft axially? Then basically you can use a set screw basically all the way through the hub, okay, and then fix it on top of the fix the set screw on the top of the key, so then you can fix the gear or any other component axially from movement, right? In the axial direction of the shaft. Okay, so that size, right? In terms of design, you can use it as reference what size of set screw that you should choose, okay, to satisfy the purpose here. Okay. So that's another information. This is not in textbook, but you can make use of if needed. Okay. One more information that this is something I will write down here. So typically the width W, okay, is taken as 1/4 of the shaft size D. So D is basically the diameter of the shaft. Okay. And there are a couple of comments here, and I wanted to make before we move on here. So first comment is the case material. Okay. So you typically you don't need to pick very expensive material for the case, and I'll explain that. The stock key materials, okay, they are typically low carbon, okay, and cold rolled steel. So typically very cheap material, okay, and very easy to find. Okay. And another thing is, okay, when you machine the key or when you manufacture the key, the nominal dimension, okay, for the key dimension basically is a W times L, W times H, right, times L. So the nominal dimension should be, okay, negatively toleranced. Okay. They should be negative toleranced. So what does that mean? Basically, for example, let's see, right? For example, let's say W equal to 1/4 inch. Okay, so you, if you pick a square key and you use a 1/4 inch for the square key. Right. So then you need to put the key into the key seat, right? Put the key in the key seat. That key, basically, the nominal dimension for this negative tolerance basically means you label this W equal to 1/4 inch, and then plus, basically, for example, plus 0.000 and then negative 0.002 inch. So that's what negative tolerance means for the dimension. Okay. So then basically now your key seat, right? The key seat on the shaft can be machined using, for example, a mill of 1/4 inch size, right? Exactly 1/4 inch size. And because the key is negative toleranced, and guess what? You can just put it right into the key seat, right? Without any, basically like a press feed or any pressure, apply any pressure to put it into it. Okay, yeah. So that's what this negative tolerance means at here. Okay. And also bearing in mind that when you design the key, the maximum length for the key, okay, so which is L, okay, that needs to be less than 1.5 times the shaft diameter D, because you just basically you don't want to have a very long key seat or very long key applied to the shaft, essentially to avoid unnecessary twist. Okay, yeah. And a couple of design things here. We're going to look at it next. So you're going to design for the key. Basically, what we're designing is we design for the length L. Okay. So the W and H often in time that you can decide very easily. So if I have a shaft of 1 inch diameter, then that's it. Then I can use a 1/4 inch W for the case, right? Yeah. And also we can look at the range of the shaft diameter and determine on the W and height H from the table. So it's the L that we need to basically design for, and the L is designed, okay, based on two different type of stresses, okay, two different formulas basically. So we're going to look at shortly. We're going to look at first, based on first is called the bearing stress, and the second type is called shear stress. So that's how we're going to decide upon the length for the K. Okay. And I'll explain what bearing stress formula, what the shear stress formulas are. Okay. And the last important point is basically you're designing the K, you're putting the K here to transmit torque. So what you really want to avoid is you want to avoid excessive safety factor for the K. Okay, so you want to avoid excessive safety factor for the K. Okay. The reason is because the K are typically functioning as a mechanical fuse. Okay. So what you want is you don't want your shaft to fill first before the K, or you don't want your gear to fill the first before the K, right, at the connection, the coupling location. What you want is you want the K's to fill. It's like a mechanical fuse, basically. The K is not expensive, right? If it failed, you can replace it easily. You can replace it with another one. So the safety factor for the K design should not be excessively large, because you want the K should fill first. Okay, so that's the point here. Okay. As you can see in our design project, we actually have two different safety factors for the shaft and for the K, and the K safety factor is lower than the shaft safety factor. Okay, yeah. Okay, so that's parallel K. We're going to come back to the parallel K shortly. Okay. The other thing is the other one here. Let's look at the Woodruff K. Just a little bit introduction at here in terms of terminologies and how you can pick a Woodruff K. Okay. Woodruff K is very much like the parallel K. You have a table that you can rely on. So this is table 7-8. Okay. So table 7-8 give you the K sate depths corresponding to the range for the shaft diameter, right, within certain range. And then what will be the K sate width? This is basically W, okay, for the Woodruff K at here. Okay. But there's a little bit more information that you need for the next one here. Okay. So first of all, let's take a look at the dimensions of the Woodruff K here. So there's a typical, basically, the drawing of the Woodruff K when your B value. So B is basically the Woodruff K is cut from a circle. It's part of a circle. B is basically the diameter of that circle. Okay, and if B is less than 1.5 inch, so that's this kind of structure right here, very similar. If B is more than 1.5 inch, and this is the Woodruff case here, right? So the only difference is basically how much distance from the horizontal diameter to the horizontal cut at here. Okay, yeah, and that parameter is defined as a E value, which is given in the table 7-7, and that's the offset value at here. Okay, that's offset E value. Okay. So if you look at table 7-7. So it gives you the K size W and the D. So this is W right here, okay, and D. I think the D here is basically the B value. Okay, so this is the B over here. This is a D. Okay. And you have the height of the case and offset, and then also K state depths. Okay, how much in the shaft? How much of the case in the hub, right, of the Woodruff K. So as you can see, you have a K height and the depths in the basically the depths in the shaft at here. Okay. Now if you add these two numbers, okay, if you add these two, for example, the last two columns, okay, if you add these two numbers, okay, that should be slightly less than this height B at here. So if you add these two numbers, you get 0.11, sorry, a little bit more than that. So that's 0.110. So this needs to be slightly more than this height. So this height is the actual height of the case. Okay, so the height of the case at here. Okay, this is the K height. So this is slightly less than what? Than the portion the depth in the shaft and the portion depth in the hub. So that essentially you can imagine you want the Woodruff key to be able to fit into the shaft and the hub key seat easily, right? Because the key size height is slightly less than the actual hub length and key seat length in the shaft. Okay, so see that's slightly more than this B value here if you add it up. There's another table in the lecture notes, which is this table here. Okay, that's basically the same value, same table as the 7-7. Okay, yeah, 7-7 here. But there's only one more good information on this table here. Is so-called the key number. Okay, key number is in industry. If you look at the catalog for the keys, okay, so that's something that you will see. It's like probably engineering language. Okay, so what key did you pick? You pick a 204. That's the key number. So based on the key number, you actually can reverse calculate essentially what is the width, what is the diameter of the key, the circle B. Okay, based on the key number at here. Okay. So I'll give you an example at here. So how you can calculate the key number essentially reads the last two digits give the nominal key diameter in eighths of an inch. So the last two digits give you the nominal key diameter in eighths of an inch. So what does that mean? So for example, let's use a key at here to illustrate it here. Okay, so let's say 406. So the 406. Last two digits, basically 6, right? It gives you the nominal key diameter in eighths of an inch. So what you do is you use 6 times 1/8, and you get 3/4. So you see that 406. So that the diameter is 3/4, right? That's how you get the 3/4 from this key number at here. And the first digit, number 4, the first digits, okay, it gives you the nominal width in 30 seconds of an inch. So give you the W here. Basically the 4 times 1/30 seconds. So that gives you 1/8. So that's your W. So this gives you the B and this gives you the W. So that gives you 1/8 times 3/4. That's how you can instead of actually spell out this WD and by just speaking the key numbers, and you can get the W value and the B value here. Okay, yeah. Okay, so that's the Woodruff key parts. Okay, how you can interpret tables for the Woodruff key. Okay. So our focus, as we call, we're going to focus on the key design at it here. Okay, the key design. So I'm going to look at the procedures for the key designs, okay. Some typical procedures and what you need to be careful with. Okay. Okay, so here's a number of steps that involved in the key design. First step, you got to be able to finish this shaft design first. Finishing the shaft design basically means you obtain the so-called minimum shaft diameter, right? So the shaft diameter is decided, okay, after you finish the shaft design. And then once you have this one determined, we can use this empirical formula to decide upon our W, okay, 1/4 times the shaft diameter. Now from here, really depends on the D size, so it could be rectangular or could be square K, right? So that's the H size. That's where you would decide on the H. So if you choose that, this is purely from the table, right? This is basically from table here. Good. So these two are easy to obtain, and then it's the L we need to design, right? before deciding for the L, we need to specify the material. Okay. Material, as I said, is typically low carbon cold rolled steel. So let's say you use a 1020 cold rolled steel. Okay, yeah, cold drawn. Now, number 4, okay, determine the SYT. Okay, so SYT not only for the K, okay, but also determine the SYT for K for shaft and the hub. Okay. The reason essentially is your K is right in between the shaft and the hub, and they're going to be basically squishing and compressing this K when torque is being transmitted, right? Yeah. So there is a possibility that somehow you pick the shaft or hub whose material are actually weaker than the case, right? It's possible. Okay. So in that particular case, you actually will see, instead of designing for the K, you're actually designing the K based on the shaft or the hub material. Okay, yeah. So whichever is the weakest material among these 3, that's the material property that you will use for the K design, the length design, okay, calculation. Yeah. So that's why at this stage, list all the properties, okay, for the 3 different materials, okay, yeah. And then number 5 this is where you ask the question: if the yield strength, okay, of this K is smallest, which typically probably would be the case, okay, then the length L is based on the case SYT. Okay. So essentially you calculate the case as it is using its own yield strength SYT. Okay. But the other extreme situation is somehow what you picked is your yield strength of hub or shaft, okay, doesn't matter which one, okay, is the smallest. Okay. If the yield strength of the hub or the shaft is smallest, then, as I said, the length L, okay, will be based on the shafts or hubs SYT. Okay. So that's the difference here. That's why at the step number 4, try to list the properties of the material first. Okay. Yeah. Okay. Once you figure out which situation you're in now, okay, so then what we need to do is, okay, we need to basically we'll need to calculate the L, okay, as I said, based on stress formula, and which I'll show you the formula shortly. Okay. So there are 2 different formulas we can use. Okay. And from here you get a minimum. You get a minimum value, okay, based on the step 6 calculation. So this minimum value is not going to be the final value you use. So for step 7, you will pick a nominal size, okay, for the length L, and that's where you basically pick a size from a stock size, right, from off the shelf. And when we have appendix A-17, I believe, there's nominal size given. Okay. Yeah. And then when you do the design, and this is basically a couple things basically need to bear in mind. Your K-seat location, right? Basically, let's see if this is your shoulder at here, okay, and we have a K-seat over here, for example. Okay. Now, your K-seat, okay, if you recall that, don't be too close to the shoulder location. Okay. Make sure there is at least d/10 of a distance, okay, to the fillet location, so that you don't have the merge of the two stress concentrations, right? Because K-seats are typically location with a very high stress concentration. Okay, so last thing that you want to remember is, which I have listed, the K needs to fill first. Okay, so the case fills first. Okay, that's the typical steps, okay, for K design. So let's jump into details here, especially the details for this step right here, for step number 6. Okay, how do we calculate this L, and what formulas we can use to calculate this L here? I'm going to look at give you 2 different cases. Okay. So let's look at the first case here. So this one here, I will call it the failure from shear stress. Okay. The failure from shear stress. Here's an illustration of what we mean by failure from shear stress. Okay. So you have a shaft over here, and then you have a case between the hub and the shaft. Okay, so the top one is hub, and this is a shaft. So there's a certain amount of torque that being transmitted. Okay. So as apparently you can see, basically the case are being pushed and pressed between the shaft and the hub here, right? Yeah. So in this particular case, number 1, what we're looking at is we're looking at this cross section. So if you expand it, basically, if you imagine, okay, so this is basically if you cut a cross section right there, right, and you got basically a rectangular cross section here. So let's call this area of the cross section AS. So that's the area of the cross section, and AS, what we define it, so it's defined basically called shear area. Okay, the shear area. So it's like you have a force pressing this way and a force pressing this way. That's like a direct shear, essentially, right? What's on that surface? You got a direct shear right here. Okay. And the shear area, apparently, you can see what does it equal to? Equal to the width of the K times the length of the K, right? So that's W times L. In this case here, let's say capital D is used as the so-called shaft diameter. Okay, shaft diameter is capital D at here. And the W is the K width. Okay. So now let's calculate this direct shear. Okay, let's calculate direct shear at here. Direct shear is the result of this force F, right? So tau equal to the F over the direct shear area, AS. And that's the direct shear tau. And what does this F equal to? F comes from the amount of torque that's been transmitted. So you transmit a torque either from the shaft to the hub or from the hub to the shaft, it doesn't matter. Then if the torque is a T, then T divided by basically half of the shaft diameter will give you this force, right? So force times the radius give you the torque, essentially. Okay, yeah. And the AS we calculate, which is W times L. A little bit simplification, you got 2 times 2 times T over dWL. So that's the amount of the direct shear on this area here, okay, on this area. Okay. So now let's see, I'm going to use maximum shear stress theory, okay, for calculation, maximum shear stress theory. And maximum shear stress theory says safety factor equal to 0.5 SYT over the maximum torque, okay, the maximum, not limit torque, the maximum shear stress. That's MSS theory. Yeah. Or in other words, okay, we can get the allowable shear stress is equal to 0.5 SYT over the safety factor N, right? So that's the maximum allowable shear stress. And here is your actual shear stress, right? Here's the actual shear stress, which is a pure shear basically. So then you let these two quantities equal to each other, right? And then solve for the L at here. So we get L equal to 4 times N times T over SYT times D times W. Okay. And that's the calculation, the minimum value for the K lengths. Okay. And when we're relying on this so-called failure from the shear stress scenario. Okay. And so it depends on the safety factor, the torque, the shaft diameter, the width of the K, and the material of the K. Okay. Yeah. Okay. So let's take a look at the second case here, and then we'll look at an example. Okay. This is a failure here is from the bearing compressive stress sigma. Okay. So it's a different type of stress consideration. This is from bearing compressive stress sigma here. So this type of a stress, essentially, if you look at this picture here, so what you consider is, instead of considering the shear stress area, okay, you consider the area on the sides, okay, the area on the sides of this K here, okay, the area on the sides. So if you look at this one here, basically, if I look at the force being applied on the side of the surface here of the K, so it's like the K are being pressed from both ends, right, from both sides of the surface. Okay. And that's what we call the bearing compressive stress sigma at here. Okay. So let's say we take one side for example at here. Okay, so that shaded area, okay, is called AC. Okay, so this is called AC at here. So AC is essentially is called the bearing area, right? The bearing area. So AC is the so-called, okay, compressive bearing area. And how do we calculate that? It's very easy. So AC is equal to half of W and then time the L, right? Times L. Not half of W, half of what? Half of H at here, right? Half of H. So half of the height times L. Okay, that's your AC, the bearing area. And then the bearing compressive stress sigma. Okay. The sigma here is just simply equal to F over AC, right? So F over AC, and F is equal to T, the same as before, T divided by half of the radius, and then divided by H over 2 times L. And this simplified to be 4T over DLH here. Okay, DLH. So that's bearing compressive stress. Now I'm going to use MSS at here. Okay, MSS. Okay, if we use MSS here, then the N value, as before, is 0.5 SYT over the maximum torque, maximum shear stress. Okay, maximum shear stress. So for this particular example here, if you take a stress element, so what you see basically, you see a stress analysis for this element. There are only compressive stress acting on both sides of the stress element, sigma here, right? And then the corresponding mole circle is basically the end of mole circle, which is on the left side of this plane and here. Okay? That's a mole circle. And then you get a negative sigma like this. Okay? And sigma is this value. Okay? This value. So based on this mole circle, what's the maximum shear stress, which is right here, right? So this is your maximum shear stress. And this maximum shear stress, easily you can see now from the dimension, this maximum shear is equal to just half of the sigma here, right? Sigma over 2. Okay? So then when you calculate, basically, when you calculate using the MSS here, and that's essentially at 0.5 SYT over half of this sigma here, which becomes just SYT over the sigma, right? SYT over sigma. Okay? Yeah. If you use von Mises stress or the distortion energy theory, okay, and then sigma prime is equal to sigma x square minus sigma x sigma y plus sigma y square plus 3 tau xy square. That's the formula for the dE von Mises stress. Okay, and if you look at this stress element, there's nothing on tau. There's only one sigma. So basically, the sigma prime in this case will be the same as the sigma over here. And dE theory, the formula is n equal to SYT over sigma prime, which is SYT over sigma. So apparently, in this case, the MS theory and the dE theory are actually result in the same formula, right, for calculating the safety factor. Okay. So if I combine the safety factor calculation with the actual stress sigma over here, basically plug the sigma here and here, and backward calculate for L. Okay. So then we can get our L, okay, which is equal to 4 times n times t over SYT times d times h. There. So now we got essentially two formulas we can make use of to calculate the minimum length for the K length, okay, of the K. If you look at these two formulas, right, for very much similar to each other. The only difference was, here's the W, and here is the H, right? Here's H. Okay. So basically that means if you choose a square K, then these two formulas are basically what? Same thing, right? Yeah. Okay? Yeah. So if square K, okay, same formula. Okay? Yeah. Alright, so let's take a look at an example, okay? Take a look, quickly look at example here. In this case here, you're asked to design a square K. So this is simple now. Okay. Here is number of parameters we know. Assuming shaft has been designed as a 25 millimeter shaft diameter, it is being used to transmit a horsepower, not a horsepower, transmit a power of 15 kilowatts. Shaft is spinning at 7200 RPM. We are going to design a K with SYT equal to 460 Newton per millimeter square. And safety factor equal to static safety factor equal to 3. Okay. So basically, L equal to what, W equal to what, and H equal to what. And that's the design question for the key. Okay, so you could look at both cases, right? Let's see if I do a calculation. Okay, before we do this calculation, we need a few more parameters here. What we have here is the amount of the power being transmitted, 15 kilowatts, and also the RPM. So we were not given the torque, right? So we need to calculate the torque first. Now this question, torque is basically the power over omega. Okay, not W, over omega. So power over omega is the torque. The formula you need to be ready, because this one is given in kilowatts and RPM. The formula here is basically 9.55 times H divided by RPM. This will give you a torque in a unit of Newton meter. Okay, Newton meter. So let's try it. So this is 9.55 times 15 and divided by 75 RPM. Okay, this will give us 198.9 Newton meter. Newton meter here. And since we're going to design for the K, it's a metric system, so I will make use of this table here. Okay, so there's a metric here. I'll make use of this table for my design. And before we move ahead, okay, and that table at the end of the selection, you will use millimeter basically. So we might as well to change this basically this torque from Newton meter to Newton millimeter, essentially times 1,000. Okay. So that's how much of the torque they're being transmitted at here. So you can now if you wanted to go through the detail, basically let's calculate what is the basically direct shear stress or allowable stress. So 0.5 SYT over N, and it's 0.5 times 460 divided by 3, right? Give us a 76.67 Newton per millimeter square. And we can also use compressive bearing stress calculation. Give us a sigma allowable, which is SYT over N, and that's 460 divided by 3, approximately 153.33 Newton per millimeter square. Okay. So that's your allowable stress at here. Okay, allowable stress. Actually, really need this one information. But anyway, so now we're talking about square K. Okay, square K here. Square K meaning W is the same as the H. So we're gonna take, let's say, 1/4 of the shaft diameter. That's 1/4 times 25, and they give us 6.25 millimeter. Okay, 6.25 millimeter. There, you never for the W and the H, you never use any decimal numbers. So what we can do is if you look at the metric system, what we can do is let's select the W and H equal to 6 millimeter. Okay, so awfully close to 6. You may argue, so why not choose a 7, right, or choose a bigger numbers? Well, the reason is, you pick a smaller number here is fine, and then we can compensate that missing 0.5 by an appropriate shaft length L, right? Yeah. So you can choose 6 at here. Okay. If you look at this table, right? If you look at the table here, there's the table. Our D is 25, so it's actually, so if you look at the D25, it has a recommended actually 8x7 at here, right? Yeah. But I guess I've been just kind of going by myself of choosing 6x6, right? So either way is fine. You can actually choose 8x7. That's okay. But 8x7 is not a square key, right? Yeah. Okay. So let's go back to this. So we picked 6 for W and H now. Okay. Now let's calculate L. Okay. Let's calculate L. Okay. So there you can use, in this case, really doesn't matter. You can use either formulas for calculating the L, because it's square K, so both formulas will actually give us the same results at here, right? So let's say I'll just use L equal to 4 times N S over T, and this is N S here is 3, right? Divided by S Y T times let's see, this is a small d we're using in this question, and then times W. Okay. So what do we have here? So 4 times 3, and torque is that big number, and then divided by 460, and then D is 25, and W is 6. Okay. And you end up with a 34.6 millimeter here. Okay, 34.6 millimeter. That's the length of the L. Okay, and if you look at table, the nominal size table 8-17, okay, then you can choose L to be a 35 millimeter. Okay, so overall your K is 6 by 6 times 35. Okay, 6 times 8 times 35. Okay. So that's K design. Okay. Any questions? Yes. Right. Custom meaning?
We're going based on stock design.
Yeah. Custom means what? You mean the shape or the size? Well, you still need to be ready for the justifying the size, right? Which basically means you still need to do calculations whether the size or whatever the shape that you designed actually satisfy the stress condition, essentially, right? And these formulas are based on the calculation. So if you have the actual loading condition, you pick this size, and then you guarantee that the key will be safe, right, within that working condition. So if you choose a different size, it depends on really what you're saying customer. If you choose a different shape, if it's not a rectangle shape, it's a completely different type of shape, right? You still need to calculate. You calculate like the way we calculated this bearing compressive stress by finding the actual area, right, being buried between the shaft and the hub, or the actual direct shear area. So you still need to calculate this. You can justify, then that's fine, basically. Yeah.
So for something like a plate key or a give key, then our area would change. That's it.
That's right. Yeah. If you're using give keys, right? If you're using give keys, you still need to basically justify by calculating the area. If you're using Woodruff key, actually the next week tutorial there's one here that will show you. If you use Woodruff key, then there's much in the shaft, there's this much in the hub, right? And you will have basically similar the bearing stress, how much here and there, the direct stress, shear stress. So there's still a calculation involved here. Yeah. Yes. Oh, is that right? Eh? That's a good point. So what? Sorry, let me just double check. Make sure I got all the numbers here. Oh, yeah, you're absolute. This is 72, right? So this should be 72 here. Oh, 15 kilowatts. Sorry, kilowatts here. So this is 10 to the power 3 times, right? Yeah.
Yeah, but I did multiply that.
Did you use 72?
Yes.
What did you get?
19.89.
19.89.
Yeah.
Missing by 1 digit? Oh, well, let me just get rid of 1 0 here then. How about that? Yeah. I'll make sure not this kind of thing won't happen in the exam for sure, right? Yeah. So anyway, instead of changing the rest of the calculation, let's just change this one to 720. Okay. Good. Yeah. Glad somebody's following it here. Yeah. Okay. So that's it. That's basically everything so far. Everything related to design projects, basically. Okay. You are completely ready for your design project. Okay. Still have a little bit of time here, so I wanted to start the bearing part of the. Actually, we still need to cover the bearing. So let's start the bearing by looking at some PowerPoint, looking at the introduction to bearings. Okay. Okay, so we need to select bearing, but let me give you a very brief introduction to bearings. The introduction meaning we need to be able to identify different bearing types. Okay, just looking at a bearing, be able to identify what type of bearing they are. It's a ball bearing or roller bearing, right? This is the trees that we have been showing. Bearings is over here. So once we finish this, we're completely finished this corner right here. Okay. Okay, so bearing is not actually new. The concept of bearing has been existed for a long time. This cartoon shows here basically in the 10,000 BC, and you can sense it to find that the rolling motion, okay, is much smoother than the sliding type of motion. Okay, yeah, and in 1000, actually, this is before even 1000 BC. In 2400 BC, the Egyptians they actually used lubrication such like water, to construct or reduce the manpower required to drag sledges, right? And this picture here shows basically in 10,000 BC, the Assyrians they employed rollers underneath the sledge to achieve similar results with less manpower. Okay, so it's basically sort of inevitable to see this modern age of the bearing type of structures starting to show up here. So bearing essentially is you have a cluster of balls, okay, within two rolling surfaces, okay, and the structure of the bearing give you a very smooth motion and give you a high power of basically speed. Okay. Here is a structure of the basically an anatomy of the bearing right here. Okay, so if you look at the number of terminologies shown in this figure, the important one here is this ball size. Okay, so that's the ball size over here, okay. And also this the outer dimension over here. Okay, the outer dimension. The other one is the corner radius, okay, and the width. Okay, so if you look at catalog, those are basically the values that you will find in the catalog. And of course the number of balls in it, and separated by the so-called cage. Okay. And often in time there will also be the seals or or shield outside this bearing right here. Okay, yeah. So this is a typical ball bearing showing right here, right? We'll see instead of balls right here, it could be also be roller. Okay, yeah. Bearings are being used to carry loads. Okay, so what do we use for? We have a different kind of loads. The first kind of load shown here is radial load. So radial load is a load being vertical to the shaft. So if you have a bearing at here, so you should use it to take the radial load, and this is the actual distribution of the load on the balls, okay, over here. So it's not a really a linear type of things, right? Another type of a load is called the thrust load or axial load. Thrust loads are perpendicular basically to the radial load, and they are in the direction of the shaft. They are often are the results of, for example, a helical gear or bevel gear. Okay, when you're using this type of gear transmitting load, then you will have this thrust load or axial load on the shaft. Okay. So you do need a bearing that is able to take this thrust load and eventually carry the thrust load to the through the shaft and then to the ground. Okay, so that's the thrust load, how to deal thrust load here. And combined load, that's very well be the situation in here. So you have a combination of radial and thrust load. So when you have a thrust load, essentially like an addition of two vectors to here. So you can see the direction of the load is slightly different now. Okay, it's in the inclined direction. Okay, because of the two radial load and thrust loads at here. Okay, so you do need a bearing that is able to take both type of loads if necessary. The type of bearings I'll show you two different ways of classifying the bearing. This is the first type. The first type is look at the types of rollers, okay, and then to categorize the bearing. So here the first one here is the ball bearing. So the roller here is the ball here, and then cylindrical roller. So this is basically a cylindrical type of structure, okay, shape. And this is a tapered roller. So the shape is, instead of a pure cylinder, it's actually tapered roller. Okay. So that's the third type. And then you have also this so-called spherical roller. So if you enlarge the surface of the roller, and that surface is actually part of the spherical surface. Okay, so that's why it's called a spherical roller. And the last one here is a needle roller. So essentially it's a sort of a cylindrical form, but it's a very narrow, very thin, and it's like a needle, but it's not really nothing, right? It's very useful if you have a limited space at the bearing location, okay? And you also want it to be able to carry a significant amount of a radial load. So, and then this needle roller bearings are the best type for that situation. Okay. So the other type of classifying is to look at basically how the bearing is being operated. So essentially like four different types of here. So the first type is radial ball bearing. So this it can take a radial load, okay, and the rollers here is all ball type of bearing. And the second one is radial roller bearing. So it's mainly used for taking radial load, okay, and the inside elements, rotating elements, are roller type of bearings, okay, roller elements. And these two here are completely different from these two. This essentially, you use it for horizontal axis rotation here, and this one here using for axial ball bearing. So the axis goes from the top, goes all the way down here, okay, or goes way through it, okay, and then you carry the thrust load essentially, okay, through this direction. There's rotation in this direction here, vertically, okay. All right, so that's the category of a different type of bearings that are here, right? Yeah. Let's look at a little bit detail into each type that are here, okay? And we'll look at the advantage of each and the applications of each. Okay. So the first one is basically what we call the deep single row deep groove bearing here. Okay. You have a rolling balls between the races, okay, and it can be used to support mainly for radial load, but it can also be used to support certain amount of a thrust load at here. Okay, so you can definitely there's certain amount, and then it can be both directions for the thrust load. Okay. For this type of bearing, the assembly here, there are two different ways to assemble it. The first one here is basically called the Conrad assembly. What you do essentially, you move the center rings away from the center, and then you put the balls into this as much as possible, and then you squeeze the ring back to the center. Then all the balls will be evenly squeezed, distributed in the raceways. Okay, so that's called the Conrad assembly. Another type of assembly here is basically you have a feeding slot at here. So then you drop the balls into the feeding slots at here. Okay. The second one, you can have a greater number of balls than the previous one. A greater number of balls basically means you can increase the load capacity, especially the radial load at here. Okay. But however, there is one shortcomings though, which is what? When you have a slot like this, and you will generate the so-called stress concentration, right? Yeah. Outside the bearing, okay, you will see sometimes, you actually probably will specify sometimes yourself into the catalog what type of a shield or seal you need for the bearing at here. Okay. Shields are typically steel stamping, okay, that covers the rolling elements. Okay. So then you're basically trying to avoid contact with outside obstacles or foreign objects, right? Yeah, to keep the dirt out. Okay. Now, if you look at bearing, sometimes you will find a notation called Z or Z or double Z. Okay, so double Z basically means that you have a double shield, both sides. There's double shields. If you have single Z, then there's one side has a shield there, right? I don't know if you play fidget spinners, you'll find that type of very cheap bearings in a fidget spinner. And if you look at on the top, you'll see it's similar, basically Z or Z to Z in a notation. Okay. Yeah. And this one shows you instead of a shield, it's using the seal. Okay. Now. Seal are made of a nitrile rubber, okay, and the notation-wise, you see if it's DU, meaning it's a single seal. If it's a DDU, meaning it's a double seal. Some manufacturers probably have a slightly different notations, though, right? Just read the catalog carefully in terms of the meaning of the prefix and the postfix. For this one here, it's actually maintaining a really good contact or protecting the bearing from contaminant. But the only thing is, you see the lips of the seal actually touching the inner ring at here, right? Yeah. So that does reduce the kind of the speed limit, okay, because of the contact over here. Okay. Yeah. So this is another type which completely has no contact. Okay, so. That's just for a higher speed application. But however, this is not a complete seal. The water could come into this inner space at here. So it's not the water resistance adequate. Okay. So that's ball bearing, deep groove ball bearing here. Okay. And this one here, a couple example of ball bearing here. This is called angular contact ball bearing. Okay, angular contact. So what the angular contact essentially is, the inner ring is essentially like a deep groove ball bearing. It's the same thing. You have a groove, you have a raceway, you have a balls at here, and it's the outer ring at here. It's slightly looks different, right? Yeah. Now, if you enlarge this contact area here, okay, if you enlarge this contact, and you actually will find that this portion at here is a point-to-point contact. Okay, it's a point-to-point contact here. So that's why. If you have a load, there is a load in that direction, right? Along this line of action here, right? So this angle, okay, is a so-called contact angle, okay? And the contact angle actually determines how much of this thrust force or thrust load it can carry, right? So the higher contact angle you have, the more or the heavier thrust load this angular contact ball bearing can carry, essentially. Okay? So this figure here shows you different contact angles, right, and then shows you the kind of the load direction, right, due to the difference of the contact angle. This picture shows you the correct assembly or application in the angular ball bearing. You have to be careful which direction is that thrust load. If the thrust load is in this direction, then you should assemble it in this way so that it can take the thrust load, right? If thrust load is in the other direction, then if you use it improperly, then the bearing actually can falling apart very easily due to the load, right, to the incorrect assembly. Angular ball bearings are often being used in a pair. Okay, so basically, if you wanted to be able to take a thrust load in both directions, then you can use angular ball bearing in a pair. There's 3 different ways of using them in a pair. But the last pair is actually only take a thrust load in one direction only. Okay, but of course, two side by side will take more thrust load. But this one here is so-called back-to-back, and this one here is so-called face-to-face. Okay, yeah. The difference is basically can be illustrated in this figure here. For the back-to-back and face-to-face. And this one is back-to-back, and this one is the face-to-face, right? So both can take thrust load in either directions. Okay. However, the back-to-back can take actually oftentimes can take more tilting moment. Okay. So basically, what it means is, imagine you have a pair of ball bearing, angular ball bearings, so a contact ball bearing here and over here, right? Yeah. So as the load is applied, there will be a tilting moment, okay, felt by the bearing at here. Okay. So when you have a back-to-back type of structure, okay, it's like you have a bigger, a waist at here, right? Like a big fat guys, right? So then it's very hard to tilt it, isn't it, right? And this one here is kind of slim, right? So that's why it's not as rigid as this back-to-back. The face-to-face is not as rigid as back-to-back. Okay? Yeah. So as a matter of fact, the back-to-back is the most popular type of structure than the face-to-face, though. Double row bearing, it's just to add another row of bearing there. So apparently when you have double row bearing, it's a little wider and you can carry more radial and a thrust load, right? But it does need more space on the shaft, right? Yeah, so it's not as compact as the single bearing. There's also the self-aligning double row bearing. So you have essentially sort of a spherical surface on the top of it here, and if the shaft, okay, due to certain extreme loading, the shaft actually bend or deflect, then this type of bearing will be able to accommodate certain amount of a deflection, which basically cause this misalignment, right, at this bearing location. Right? This is single direction of thrust bearing. Okay, so it's just basically make sure you don't use it for a loading condition that's like this, right? Yeah. So it's not suitable for taking radial load, basically. Okay. And this is a single direction of thrust bearing here. Just kind of shows you how to achieve a degree of extreme aligning ability. So the thrust ball bearing sometimes mounted on the spherical seats. So you have a spherical seats over here. Okay. So that give you certain degrees of freedom in terms of handling the misalignment or deflection. So those are ball bearings, right? Those are ball bearing here. Okay. There's also the roller bearing. So let me just cover a couple slides and then call it a day here. Okay. This one is a cylindrical roller bearing. There are different type of cylindrical roller bearing labeled by basically different different names. So this is N, NU, as you can see. the end here has two flanges on both sides here, and then there's no flange on the top. But NU is essentially the opposite of this, right? So the inner ring has no flange, but the outer ring has flange. Ball bearing, roller bearing can take a certain amount of thrust load, but not as much though, right? So it's really good in terms of handling the radial load. So if you see a number, like if you see a symbol like NF, NJ, you can see essentially this is the difference, right? So NF has a flange on this end, there's a one flange one end, but then there's a flange, no flange over here. And that's NJ size here, right? Okay. So basically for the NJs, for example this type, you're not supposed to apply a load in this direction, right? Otherwise it'll fall apart. It'll be falling apart basically. Okay. Yeah. So I think I'm going to stop here. There's a few more slides here. I'll be quickly finished in the next lecture. Okay. Yeah. And then we'll look at the selection, the procedure of selection bearings. Yeah. Any questions? Okay. Good. How are you?
Doing all right.
Good.
Quick question for you in regards to
Yes.
when you're talking about the shear area, you're just drawing a straight line across your shear area.
Yeah.
Wouldn't it technically be the arc, right?
No, it's it's very small, right? It's very small.
Yeah.
So
Straight across would be
right.
almost equal to the arc.
That's right.
Anyway.
Yeah. So you basically you consider the cutting edge, right, horizontally through it.
Okay.
And that's our sort of assumption we made because the force one here, that's the one here, right? So it's like you're
Right.
sharing it.
My thought was that at this point right here,
Yeah.
if you draw a straight line from here to that point,
Right.
it's actually off at
That's right.
at tangent a bit. So
Yeah.
my thought is that if you continue that around, it would be
Yeah.
along an arc instead.
Right.
And
So-
when keys fail, they're sheared along that path, aren't they?
Could be, yeah.
Okay.
Could be, but I guess because it's so small, you can argue, you know,
Okay.
instead of using that area, you can,
Just because it's thin enough in the arc angle.
yeah.
They'll be
Yeah.
close enough. Okay.
Exactly.
Okay, just approximated it straight.
Very good.
Okay, awesome. Thank
Yep.
you.
You're welcome.